So I think even though it's not yet 11:05, but everybody seems to be so disciplined, so let's not take the time away from the second talk. So there will be the first talk, also in a series of 4 talks by Jacques Tilouine from Paris 13 in France. And he will give a series of lectures on integral period relations for base change. Okay.
Thank you.
You're welcome.
So I start by motivation. So I take 2 number fields, F and E, and I take a motive M defined over F with coefficients in E, and which is pure of weight 0. So, for instance, if you take the line given by with action by a character, so the E line with action by a Hecke character of F of finite order. Or you take an elliptic curve defined over F, and you take the adjoint motive, which is the endomorphisms of trace 0 of the cohomology of the elliptic curve. So this is over Q. So this is so here E is Q, for instance. Here E is E. Well, of course, you have a dual motive, M dual, which is Hom ME. And it is also of weight 0. So for instance, the dual of this one is E of chi minus 1. The dual of this one is itself. So this is self-dual. And so if chi is quadratic, this is also self-dual. So let's take a alpha quadratic character of F. Then this is self-dual, and also the twist is also self-dual. So these are examples. So we fix an embedding of E into C. So we have the L function. So I complete the L function by the Euler factor at infinity. Then I denote it by lambda. So this is the completed L function. Then you know that there is a conjectural functional equation relating lambda M 1 minus S and lambda M dual of S by some non-zero factor. So it is conjectured for such a motive of weight 0 that the value at 1 is non-zero. So it is conjectured that the value at 1 is non-zero. And yeah, so we fix also a p-adic embedding for some prime P. And so we have a place V here corresponding to this embedding, p-adic place. Then we have the v-adic realization. So this is an EV vector space. We fix a lattice inside this v-adic realization. So this is a Galois F bar over F module. So I denote this by gamma F. And so it's an OEV module, pre-finite rank with the action of Galois. We also consider its dual, and we can define the Selmer group of this lattice. So it's a sub of the Galois cohomology of TV tensor EV modulo OEV, which is a divisible thing. So this thing has finite. Well, no, this is huge, but Selmer is a sub which has finite corank. And question mark means nothing or dual. And so we can also define, so this is defined by Bloch-Kato, let's say, or by Greenberg in the ordinary case. So this is Bloch-Kato-Selmer group, or Greenberg. They are compatible so Greenberg is an ordinary case. So we can also define, this is defined by Bloch and Kato, a period, which I call omega, well, I could Bloch-Kato or motivic also, of M, but actually, well, M, it depends on the choice of the lattice. So this is a number up to a unit of the localization of the ring of integers of E. So these are defined by Bloch and Kato in their famous paper in the Grothendieck-Festschrift. And there is a conjecture of Bloch and Kato, which I like to state this way. So first of all, because of this, the conjecture that Selmer is finite, but actually Selmer dual. Because you see, we will work at 1, and their formulation is at 0, which involves the functional equation. So there is some small, so this is Bloch-Kato plus Poitou-Tate duality, which says the following. So Selmer of TV, what was my notation? So, yeah, TV dual is finite, and the cardinality, it's not the cardinality, this is a finite OEV module, and so you can define its OEV cardinality, which is you take a uniformizing parameter to the power, the length of this finite module. I call it the cardinality. So the cardinality of Selmer, TV dual, is equal to the value at 1 divided by the Bloch-Kato period, depending on the lattice. Well, actually, it's the, well, I write like this, okay, but it refers to the dual. But I write like this because I take M at 1, so I call it the period for M at 1. And that should be this number. So this is the conjecture. When I say equal, of course, it's up to O, E, V cross. And this conjecture is usually inaccessible. And so we study automorphic Ersätze, substitute. And so, but okay, so what application can we find for knowing such conjectures? You see, if you look at the definitions of these objects, it's rather functorial. And so if you have a decomposition of the motive M, you will, and decomposition of the lattices TV, the lattice TV, you will have factorization. So assume that M is a sum of two motives of weight 0. And from now on, we assume all the motives to be self-dual. We will deal only with self-dual motives. So Mi dual is Mi. We fix lattices, what is my notation? Yeah, TIV inside MIV. So we assume we have a decomposition. So we fix these lattices. So we have a decomposition by definition. So in this situation, so everything is weight 0, pure of weight 0. In this situation, you will have that the Selmer group decomposes by definition. The periods decomposes. Okay. The L values decompose, of course. Therefore, if you know Bloch-Kato conjecture for two of the motives, you know Bloch-Kato conjecture for the third. Okay? And that's exactly the situation we will investigate, but not in the motivic context, but in the automorphic context, where all these objects are more accessible and things can be proven. So we will have to replace these periods by automorphic periods. These groups or their cardinalities by congruence numbers, which are substitute for this. And in some cases, one can prove that these congruence numbers are equal to the cardinality of Selmer. And so we will have theorems in the literature proving exactly this when you replace Bloch-Kato by automorphic and this by congruence numbers. And we will have factorizations. So the factorization of congruence numbers is slightly subtle, but we will have some sort of factorization. And we will deduce. And the context of decomposition will occur in the base change situation. We will consider a base change situation, and we will have a decomposition given by base change. And basically, we will know the automorphic analog of Bloch-Kato for two of the motives, and we will deduce it for the third. In some cases, or we will conjecture it, but we will prove something even in the direction of the conjecture in different contexts. And we prove completely this in one case with Eric Urban in a previous work. So what is the automorphic analog of this? So the automorphic analog is to consider a transfer So we take G connected reductive group, let's say over F, so quasi-split, well, let's say over Q, and well, it could be over F. Yeah. That would be the F. So we have the L group, which is the reductive dual semi-direct with Galois of F bar over F. I am a bit imprecise. So E will be sufficiently big to save time. It will be already a p-adic field, okay? It should be a number field, but okay, sufficiently big p-adic field. It's the completion. Think of E to be the completion EV, okay? But big p-adic field. So it plays the role of the coefficient field. We start with pi cuspidal cohomological on G of A, the others, G of AF. We assume that there is a Galois representation at V. So V will be, V will be the p-adic field. Valuation V. So we assume that we have the Galois representation. So from gamma F, gamma F to LG of O. O will be the valuation ring of E. And so for us, the TV will be the adjoint of rho V. So what is the adjoint of rho pi V? So what does it mean? It means the following. We consider we consider the Lie algebra of the dual reductive group over O, and we take the derived group. Okay, so this we denote by G hat. So derived means a semi-simple part. Okay, we take the just like when you had an elliptic curve, you took the cohomology, you took the endomorphism, but you took trace zero. Trace zero is so this is SL2, okay, inside GL2. So this is the semi-simple part. So that's what we consider G hat. And so there is an action of LG on G hat, which is so this is the adjoint action, okay? And now we have the Galois representation from Galois to LG. And so this becomes, so this is a finite 3O module. And this becomes a Galois module. So this will be our TV. Okay? And inside, so something which should be the v-adic realization of a motive, but well, this is just an adjoint of rho pi with coefficients in E, okay, which is some E vector space. Okay. As Langlands conjectured, this should come from a motive. Okay, so. No, well, I did not add. You see, add means this action, and this is semi-simple, as I said. Where? Here. This is semi-simple. So this is the add zero. But I write it add. Yeah. Okay, so this is the substitute. And you see, this is my canonical choice because I fixed this integral representation. So from now on, I drop the reference to the lattice because the lattice is given by the Galois representation. So I will define periods and so on without the reference to the TV, which will be understood, okay? Anyway, so this is the TV. If you want to know what is the TV, it is given by this integral representation. It looks like there is a choice, but actually there won't be a choice because I will assume that the residual representation has large image, and this fixes the lattice. There is no choice for the integral structure of the Galois representation. Okay, just like, well, if you have a residually irreducible representation in GL2, there is only one lattice up to homothety inside GL2 of QP, which is inside QP square, which is stable by the Galois representation in case of residual irreducibility. So that will be the situation here. This lattice will be canonical. So, and in many cases, it is proven that the L value, L adjoint pi 1 is non-zero, is proven in many cases. And as I said, this kind of theorem that so I will have to define this, but I will define it progressively, okay? The automorphic period is equal to a congruence number. So this is the key, see the starting point of our work. This is proven for several groups. So this is the congruence number, and this is the substitute to the cardinality of Selmer. So it's well, sometimes it's called congruence number, sometimes it's called congruence ideal. Basically, it's an ideal in OEV, in OE, yeah, in O, in O, well, OEV. Anyway, this is up to unit. So this is proven in many cases. And so now what is the situation we consider? So now let's say that F is Q. Yeah, of course, this is the introduction. Yeah, of course, I will explain theorems about that. I mean, I'm just describing what we are trying to do and why we are trying to do that. So now we consider two groups, two connected reductive groups, and we assume we have a homomorphism of groups, let's say algebraic homomorphism between these algebraic groups, which commutes to the projection to Galois. This is called the transfer homomorphism. And so, or base change homomorphism. And so we start with the first motif, which will be M1, if you want, in my terminology of the beginning. M1 is add rho pi. We start with a pi, which is on the H. Okay, pi is here. Pi is cuspidal cohomological on H. AQ, because now F is Q. And then we assume that the transfer is established. Assume that there exists a pi which is, so it's an assumption, it is cuspidal and it is cohomological on G such that pi is the transfer of small pi. In other words, so what is the meaning of this? The meaning is that the Galois representation associated to pi is nothing but the composition of, so you know, rho pi goes from gamma f to LH of O. Then you have phi going to LG of O. And so this should be rho capital pi. So we assume that the transfer has been established. Okay? So this problem, find capital pi such that the Galois representation is this, has been solved. There exists such a pi, such a packet, but yeah, for us it will be just and so of course add rho pi will be the motif M capital pi. So this is the big motif, M. This is the M. This is the M. This is the M1. And now there will be an M2. Why? Because, oh, please note they are self-dual, okay? There is an M2 because we have a situation as follows. We have G hat on which acts LG, but there is this map phi, and we have rho pi from Galois Q here. So you see, as you know, this is an irreducible or generically irreducible representation of LG. But if you restrict it to LH, this is maybe no longer irreducible, and actually it is not, because you can take the derivative of this map, which defines a homomorphism from the analog of G hat for H to G hat. Here you have this action, but actually you have also an action here, and this is compatible. In other words, G hat contains H hat as an LH module. So as LH module, you will have a decomposition of G hat as phi of H hat, but well, in our cases, this will be a simple group. This will be simple, therefore, this is irreducible, and so this is injective. So this is the derivative. It will be injective, okay, because this is simple. Therefore, you can decompose as this plus something, and this something will play the role of M2. This will be, so this is the lattice T, this is the lattice T1, and this is the lattice T2. And so we have this situation. So we know that Selmer decomposes. That's nice. And we can forget about dual because this is self-dual, okay? So there is no need of dual. But again, to talk in the language of Selmer groups is, will be a kind of a last step. Because as I said, we won't use Selmer groups, but they're automorphic substitutes, which are congruence numbers. So we will be in situations where dagger, which is maybe still there, maybe not, no, dagger is here. So dagger will be established for this and for that. And we will define the automorphic periods and try to prove the factorization of the automorphic period. And if we can do that, we will establish dagger for this one. Okay, that's the story, how what's going on in these lectures. And that's it. So we will need now to study automorphic periods. I think that's all for the introduction. So we fix a subring in C, which is a PID. So basically, it's a discrete valuation ring. And so we consider two homodules of rank 1. Well, I will say soon that you don't need to assume rank 1, but in our situation, there will be rank 1. And we assume that we have an isomorphism iota between these two complex space. And so when you have such a triple, L1, L2 iota, you define a period omega 1, 2 belonging to C cross modulo O cross. How do you do that? You pick bases and then you consider iota of delta 1 and you express it in terms of delta 2. So that's the period. Well, of course, delta 1 tensor 1, delta 2 tensor 1. Okay. When you extend the scalars, so that's the definition. So first example, assume that iota descends to O. Example 1, assume that iota is equal to iota O tensor identity of C. Then this is the situation which is uninteresting. Then, of course, the period is 1. Because you don't need this tensor, and iota delta 1 will be, so this is an isomorphism between L1 and L2. Okay, so it sends a basis to a basis. Then there is nothing. It may happen, but that's not the most interesting case. So take another example. We take C cross, which is P1 minus 0 infinity. And we take we take an integral structure. So this is the scheme GM over Z, which is the spectrum, or which is P1 over Z minus the divisor. This divisor is It's a divisor over Z. Okay, this is 0 plus infinity. And so you take L1 to be the log-Durham cohomology of this scheme. And as you know, this is a Z module of rank 1 generated by dZ over Z. Yeah, the definition, if you want to know, this is the H1 of the Durham complex of P1 allowing poles, logarithmic poles, so log poles along D. So you take this logarithmic Durham complex, and you take the H1. So this is a module free of rank 1. And so that is L1. So this is our delta 1. And you see here we have a very canonical basis. And because of that, our period will have no ambiguity at all. Because we choose this basis, and the L2 is H1 of C cross Z, the Betti cohomology, which is, as you know, generated by one element, which is, maybe I call it a C dual. Well, this is delta 2. This is the dual. This is the dual of, you know, this is C. You take one round around 0. This is the basis of the homology, and the dual, which sends this C to 1. Okay, the dual basis of this basis of the homology is delta 2. And then iota is the Durham isomorphism, Durham comparison. Iota is Durham comparison isomorphism. And as you see, omega 1, 2 is 2 pi I. If you want to see the formula is integral over C of dZ over Z equal 2 pi I. So this means exactly that. Okay. So that's more interesting. And now we will give automorphic examples. Plenty of them, because we will need them physically. So the first one will be to replace C cross by the modular curve. So we take G to be GL2 over Q. I am a bit, I'm trying to save time. So there is a modular curve. So I take the group gamma 1 of n. So there is the modular curve y1 of n. So n is at least 4, I think. So that there is no torsion. I think so. Then there is the universal elliptic curve. Then there is, of course, there is the completed. So this exists over Z of 1 over n as a smooth scheme. There is this, there is pi, there is the unit section, and there is the cotangent bundle. So we take E upper star. This we denote by omega, and then we denote by omega k. This is a line bundle over the modular curve. So we have these line bundles for any k in Z, by the way. Okay, I try to be quick so that I reach some point. And it extends canonically into a line bundle on the completed modular curve. So we will have one interesting integral structure. I am, inside the analog over C. And then there is a map from the space of cusp forms. Gamma is gamma 1. And here there is an integral structure, which I denote by SK gamma. So here we are over Z. Basically, we want to go over O. So Z of 1 over N is contained in O because I take P, which does not divide N. And O for me is you take some number field E and you localize at V dividing P. Okay, this is the kind of situation I am interested in. So you have this integral structure inside this. Here you will have the cusp forms with Fourier coefficients belonging to O. This is the choice I make of an integral structure in this C vector space. And this is an integral structure, as you know, Shimura's book. So we have two complex vector spaces which are isomorphic, as you know. This is some sort of Eichler-Shimura, but it's coherent Eichler-Shimura. I'm sorry, zero. Okay, I'm sorry. Well, I am not so sorry. This is interesting. So I call it zero coherent. So this is my iota, but of course, these are not one-dimensional, okay? But I choose some form, F, which is a common eigenform for Hecke operators, F, belonging to this, actually belonging to that, because by Hecke theory, if a form is a common eigenform for Hecke operators, if you normalize it, which means if you choose A1 to be 1, then all the Fourier coefficients belong to some ring of integers. Sufficiently big, as I said, sufficiently big PID, or DVR, inside C. So I choose one. So that will be my L1. I choose one modular form, which is eigen, just like I said, pick pi, so pick F. Pick F. F is a new form for gamma 1n, eigen, okay? So with A1 equal 1, then I consider OF. This is L1. And of course, I have a basis F. So this is delta 1, if you like. And on the other hand, you have this map, iota. I could give you a formula for this map. If you know the transcendental description of the universal elliptic curve, namely gamma under h times c over z square projecting to h modulo gamma, which is y1n. Here you have to say what the action is. You have to use the automorphic factor to the power plus k. Okay? The action is gamma acting on z v will be gamma of z j gamma z to the power k v. So, and of course the action on the action here is z v comma ab, some integer, will be z comma v plus ab times z1. Something like that. Product of matrices. So AZ plus B. So if you do that, this is the description of the universal elliptic curve. And so the cotangent bundle, oh, I'm sorry. Yeah, so this is omega k. Okay, oh, I'm sorry. So this is omega k. I am describing immediately omega k. You forget about that. This is omega k as a line bundle, okay, given by this. Yeah. Okay. If you do that, the definition of the map is as follows: is f. So if I take f here, the image will be f of z dv tensor k. I think something like that. Maybe you can put a 2 pi I to the k in front. So this is the description of this map. Okay, so there is some iota. And so, so what do you take on the right-hand side as a basis delta 2? Well, as I said, there is an integral structure. Here we are in a degenerate situation, because if you consider what is this integral structure, it corresponds exactly to that integral structure. So, okay, you look at the neighborhoods at infinity, you will see that they are given by O double bracket Q, and that's exactly the ring where the Fourier expansion lives. And so, you know, you will have a formal spectrum of this for the neighborhoods at infinity. And so this situation is that iota 0 coherent descends. So there is no period. So the period in this context, so L2 basically is just iota 0 coherent of F, and that's it. And so the period in that situation, which I call omega 0 coherent, is 1. So nothing interesting. But there is another one. That's why I wrote erroneously H1. There is another one which is more interesting. Namely, you start again with SK gamma, same integral structure SK gamma O. And here you take H1 x1n over over C omega 2 minus k, and here you take the integral structure, which exists, okay, but as I said, omega 2 minus k. But there is an isomorphism here called iota 1 coherent. It is given by duality. You have to mix Peterson duality and Serre duality. In other words, you use Hodge decomposition, and you use Poincaré duality restricted to Hodge decomposition compared to Serre duality, which is integral. And so this map, I can write the formula somewhere. I'm not sure it's here. Yeah, maybe it's not here. So you will have iota 1 coherent of F paired with iota 0 coherent of G. Serre duality is equal to F G Peterson, something like that. And this is the definition of iota 1 coherent. It is the thing, it is the thing which is Serre dual to this pair, which realize this Peterson pairing for any G, okay, for any G. So you can define that. But then the period is not 1. There is another period, which I call omega 1 coherent, and that's an interesting number belonging to C cross modulo O cross. And so now we go to the Manin periods, classical Manin periods. So we take again SK gamma. We have the same integral structure. Here we take the Betty cohomology of the modular curve, Y1n, with the notations of Raghuram. That would be Vk minus 1, well, dual if you like, of C, okay? And in that, you have something which is H1 Betty, Vk minus 1. Well, these are not my notations, but for the moment I use that. But I prefer to write K minus 2. Okay? I prefer to write the highest weight, dominant highest weight of the representation, which is not K minus 1, but K minus 2. Okay, for the moment I write like this. Okay, so, and you have an Eichler-Shimura isomorphism, but as Raghuram pointed out, you have to be a little careful. So first of all, I take the lower Schritt cohomology, which means the image of the compact support cohomology. And then there is an action of the Archimedean Frobenius on this. So there is an Archimedean Frobenius acting on this couple, and there is a plus and minus part. And so I take plus or minus. Then you have an isomorphism, which is the epsilon Eichler-Shimura isomorphism. Epsilon is plus or minus 1. And so, well, as you know, the formula is f goes to f of z x minus zy to the n. Okay, n is k minus 2. That's my favorite notation, dz. Then you take the epsilon projection. So you apply the epsilon idempotent, and that's the definition of iota epsilon. And so if you do that, you have a triple. So what is, of course, you pick one eigenform. So you pick L1 to be OF inside this, some eigenform. And here you will have so you have an action of the Hecke operators here. You have the F part. So the F part of this one, so you take the F part of this one, which is one-dimensional. So let's write only H1 lower shriek O and take the F part, epsilon, and this is O delta 2 or delta 2 epsilon, depending on epsilon. And so that's the second, so this is L2. And the isomorphism will tell you that, because of course, this is Hecke equivariant, so F part, which is this, goes to F part, which is C, of course. So you will have a period, omega, which I call omega epsilon F. So iota of delta 1, so iota of F if you want. Iota epsilon of F is omega F epsilon delta 2 epsilon. So these are the Manin periods. So you have omega F plus and omega F minus. You have two of them. And if you compare Poincaré duality and Serre duality, you will get the formula, which is the first period relation we have, but which is omega 0 coherent multiplied by omega 1 coherent must be equal up to unit to omega plus omega minus. Of course, this is 1. So you have this relation. Archimedean Frobenius, Hida, Blue Book. It's a long story. Well, basically, if you want, it's z goes to minus z bar that you have to, and then you have to define it on the sheaf also, because it has to act on the pair, okay? On the pair, this and that. So basically, on the upper half plane, it is the Hecke involution, and on the sheaf, it's basically given by this matrix. So I need three more, yeah, maybe two more periods. So you see, I would call what I did for the moment comparing the integral structure of type Fourier coherent and then Fourier-Betti. Now, there is also same Fourier coherent and Fourier-Betti for Hilbert modular forms. I will be very brief. I take F totally real. I take G, the degree. IF, the set of embeddings into R or C, whatever, or maybe Q bar, Q algebra homomorphisms. Then you have, well, you have, and you take a group without torsion. So you have a Hilbert modular variety, which is smooth. I assume there is no torsion in the group. You will have the universal Hilbert-Blumenthal-Abelian variety. You have the omega, which is E upper star of omega A over Y. You have the decomposition into line bundles given by the embeddings. You have omega k, which is k is a sum of k sigma sigma for sigma in IF. You have omega k, which is the tensor of omega sigma to the k sigma. You have, well, maybe I skip the, so you will have the space of Hilbert modular forms. And again, you have the structure given by integral Fourier coefficients for the Q expansion at infinity, let's say. That's enough. But you have also on the cohomology side, so I skip the Fourier coherent thing. I go directly to Fourier Betty. So I take the Betty cohomology of middle degree of the Hilbert variety with coefficients in the sheaf Vn. So now I go back to my notations. So K is n plus 2. What does it mean? It means that for any sigma, K sigma is n sigma plus 2. N sigma is a non-negative integer. And so Vn is, as usual, a tensor of Vn sigma sigma for all sigmas. This is, if you like, this is sim n sigma of O squared. This one, okay? With action of gamma by the sigma embedding, okay? And you take the tensor product, then you have this, and of course, this has a large rank, but you can decompose it by using the action of O2R divided by SO2, O2 of F infinity divided by SO2 of F infinity, which is the Wiles group, which is plus minus 1 to the power D, which acts on this. So you can define the epsilon parts for all characters of this finite group, and then you have iota epsilon isomorphism. This is Eichler-Shimura for the epsilon part. And you take an eigenform, so you will have OF, so this is the L1. Here you have an action of Hecke operators. You take the O integral structure, it is preserved by Hecke operators, and the F part of the epsilon part is rank 1, and that's L2. So L2 will be O delta 2 epsilon. So L2 is HD, maybe lower Schrieg, HD lower Schrieg of O, epsilon, and F. Sorry? Yeah, of course. Yeah, of course. They are all congruent modulo 2. Yes, indeed. True. You need that all the K sigmas are congruent modulo 2. Otherwise, it is not cohomological. Yeah, so, okay. Now we reach the last one, which is very important. So the last one is the periods of Balasubramanyam Raghuram, both in the room. So this time, on the left-hand side, we will deal with Whittaker integral structure, and on the right-hand side, Betty integral structure. Yeah, so I take G here. We take the reductive group to be a restriction of scalars from F to Q of GLN. F is a number field. Well, yeah. Okay, let's say that F is well, it could be either totally real or CM for me. Okay, totally real or CM. Mostly CM actually, or CM. Anyway. So then we take a pi, which is cuspidal cohomological, so which means that it occurs of weight lambda. So lambda for me is the analog of n, so it's a dominant highest weight for the group G, and the Borel that we fix let's say standard Borel. So we will have the cohomology okay, what is Y? Y is a space associated to, so GQ under GA over center, maximal compact, and some compact open subgroup of the finite adels. Okay, so this is Y, and I will take V lambda. As explained by Raghuram, you can make this O or C or whatever. You can make this as a sheaf. I have to say something that if you want V lambda O, there is an assumption, which is that the P part of the compact open group is integral is contained in G of ZP. You need that. And then it acts on V lambda O. O is p-adic again. O is, let's say, is the V completion of a ring of integer of a number field. Then you can consider these cohomology groups over O or over C, of course. Well, this is very big. It contains the Eisenstein cohomology that Raghuram likes to study. Yeah, let's consider only the cuspidal part. So we have a Whittaker model for pi. Sorry, you like also the cuspidal? Yeah, yeah, cuspidal forms are very nice. Yeah, okay, sorry. So you have a Whittaker model. So you have the Whittaker transform, which is basically phi goes to integral of a phi of ng psi bar n of g, sorry, of nu of n dn. So integral over n of a q, the n of q. So we have inside G, you have the standard Borel, which decomposes as torus and unipotent radical. And psi n is the standard integral, additive character. So this is W pi. And so we use this map, we use this map to normalize automorphic forms. So these are automorphic forms. And so we need also to fix a level. I said U, but for our work, it is important to choose U to be Mirahoric at places, at ramification places. So you have the mirabolic subgroup. The mirabolic subgroup is GLN minus 1, 0, 1, something. So this is called the mirabolic subgroup inside GLN. And the mirahoric is the matrices inside G of, let's say, Z hat, which are congruent to something like that, modulo, okay, you have a level, so you have a level, say level n, G congruent to something like that, so maybe M in something like in the mirabolic modulo n. So this group is called the mirahoric of level n. And it is known that if you choose pi of analytic conductor n, then it has mirahoric level n. Okay, it's a theorem of Jacques, Piatetsky, Shapiro, Sharaika. If n is a conductor of pi, then pi fixed by this mirahoric group is dimension 1. Sorry? Pi finite. Finite part. Okay, so we fix such a level. We need that. And then we fix an automorphic form. So we need to fix L1, okay? L1. So that will be a subspace of the space of automorphic forms. And what kind of space? It will be just O phi, pi 0. And phi 0 is an automorphic form belonging to pi, which is at finite places, at unramified places. This is just the characteristic function of G of okay, phi q, G of ZQ. And at ramified places, this is the so-called new vector. So this is a vector belonging to this space. But then you need to normalize it. And you normalize it by asking that its Whittaker transform at 1 is 1. Okay? You take that phi 0 of, so Whittaker of phi 0 at ramified, for Q ramified. You take a new vector and you assume that this at 1 is 1. This fixes perfectly phi, and this defines our integral structure. Then you have, I may not have full time, then you have an Eichler-Shimura isomorphism, which I have to normalize, so I have to do that next time. So iota will be Eichler-Shimura, but I have to explain that. Of course, if the field is real, you will need to take epsilon branches. But if not, let's say if it is CM, there is no problem. So you take just iota, and the theorem that we used by Borel-Wallach is that the top degree cohomology of cuspidal of V lambda C is pi part, is dimension 1. Maybe I will come back to that. So that will be, so this is L2 tensor C, and you can define this over O, so that will be L2. L2 will be H top of Y V lambda O pi part. As I said, this is in the case where the field is CM. If the field is totally real, you have to take epsilon parts. And that will be L2, which is rank 1, so that will be O delta 2 epsilon. And this defines the, I say top degree of cuspidal cohomology. There is also bottom degree. Why only bottom and top? Because they are the only ones which satisfy this one-dimensionality. You have a lot of interesting cuspidal cohomology groups of degree I, but only the bottom and top are one-dimensional. The other ones are have higher dimension. And we want something one-dimensional, so we take bottom or top. So we will define periods omega bottom, possibly epsilon pi, and omega top, possibly minus epsilon pi, plus or minus. And these are the Balasubramanyam-Raghuram periods, which are normalized up to unit, okay? Up to unit. So we define these periods using bottom or top degree cuspidal cohomology, fixing a nice Whittaker function on the left-hand side, and fixing a Betti basis on the right-hand side as usual. Okay, this is the usual Betti basis, and we compare them by the normalized Eichler-Shimura isomorphism. Because everything has to be normalized because we are talking about integral structure. We don't want to have an ambiguity by a complex number. So, okay, and these are the periods which, okay, I will give more details.
Okay, thank you very much for your talk. Are there some questions at the moment to Jacques Tilouine?
For people who haven't heard this, that word mirabolic comes, this is due to Jacques. It's a miraculous parabolic.
Yeah, I know.
And
Well,
yeah, so of course, you know, just for people who haven't heard this. So that mirabolic comes out of miraculous parabolic. There's something
because
very special.
yeah, you had Iwahori
Yeah.
And so Iwahori parabolic, and then yeah.
That and then
Then there is
mirabolic and
Iwahoric.
Iwahoric became mirahoric. Yeah, that's the etymology of.
Thank you. No further comments or questions? Okay, so if not, let's thank Jacques Tilouine once again for his talk, and let's thank also Raghuram once again.